Current large language models are limited by the token bottleneck. Forcing a system to translate every internal calculation into human-readable text causes processing lag, linguistic redundancy, and semantic loss. Research is now shifting core processing out of explicit language and into continuous latent space to preserve high-fidelity information. This comparison highlights the difference. On the left, explicit generation relies on a linear, step-by-step node output. On the right, latent computation allows for a thick, continuous, high-bandwidth data stream. Using latent space as a machine-native substrate allows internal processes to be carried out more naturally. This infographic organizes the latent space landscape. The first axis defines mechanisms, detailing how systems are built, specifically highlighting compressed and adaptive computation methods. The second axis tracks abilities, categorizing the functional gains enabled by these mechanisms, spanning from reasoning to physical embodiment. Mapping these mechanisms against abilities moves AI engineering from experimental heuristics toward principled architectural design. Moving beyond text-based operations provides a more flexible interface for allocating computation, particularly in multi-agent systems. As shown here, agents can now communicate by directly exchanging their internal KV caches. This bypasses the text translation step to increase the bandwidth of the information exchanged. This capacity extends to physical interaction. Vision language action models use these continuous representations to support spatial imagination and grounded action in real-world environments. By coordinating language, vision, and action within a shared latent space, models can integrate heterogeneous forms of information without the loss associated with text conversion. This chart plots the exponential increase in latent-level research, moving from early textual reasoning prototypes to the current outbreak across diverse application paths. This growth suggests a transition toward models where the primary system core is intrinsically latent. When reasoning is internalized into continuous hidden states, the system becomes opaque. This makes it difficult to explain specific conclusions or trace how information is transformed during computation. Developing probing methodologies that work natively with these continuous variables is necessary to make latent computation observable and steerable. Establishing a principled theoretical understanding of these processes is the next step in latent research. Access the full framework and repository to participate in the development of these systems.